So, we had derived boundary condition on magnetic field. If you have a surface, on that surface you have some current, surface current, then how magnetic fields on the two sides of the surface just above and just below are related, that we were discussing. And we did it for the normal component, and we found that the normal component is continuous. As you cross the surface from one side to other side, the normal component does not change. B1n is same as B2n. For that, our process was this magnetic flux through any closed surface is always 0. This was the starting point, and this comes from divergence of B is equal to 0 always. And then we took certain particular the surface and closed surface, and then using this, that this has to be 0, we showed that the normal component does not change as you cross the surface, even if there is a current on the surface. Now, the tangential component, how the tangential component is related, and tangential component is not unique, because if you have a surface there is a unique normal, but then perpendicular to the normal there are so many infinite number of directions. So, what we will do is we will find the tangential component parallel to the current and perpendicular to the current. Okay. So, that means if we have let us say this is the surface. Remember, our surface which carries current may be of different shapes, not necessarily plane surface. The current density need not be constant. So, but we are interested in some small part, because just above this and just below this, these are the points we are looking for, just above the surface and just below the surface, and the current is this way. Suppose the current is this way, x direction. Then if I take a direction parallel to the current above and parallel to the current here, and then ask what is the component of magnetic field in this direction below the surface and in this direction above the surface, how are they related? That will be our first task. Our next task will be, we will take tangential on the surface, but perpendicular to the current, that we will again do, but let us first do this. Now, for that what we will be doing, we will be using Ampere's law, and that is B dot dl on a closed curve. Remember all these things. This equation that we are writing here, this is flux of magnetic field B dot dA on a closed surface. We took the example of a cylindrical surface, flat surface, another flat surface, curved surface. So, closed surface, this equation is to be used on the closed surface, and this equation is to be used on a closed curve. So, there is a curve, and on that curve we B dot dl, B dot dl, B dot dl we will do, and this is equal to mu naught times current enclosed. And remember, I repeated several times that once you have a closed curve, you have some area bounded by that closed curve. This side, for this side you have to look at that area. For this side you only have to look at that boundary, this curve, closed curve, but for this side you have to see the entire area and how much current is crossing this area from one side to other side, that is here, and the positive direction and negative direction are decided by this arrow. The way I have put the arrow now, your positive direction will be away from you because it is clockwise. So, the positive direction is behind the board. So, how much current is going from our side of the board to the other side of the board, that has to be written here, because that also decides the sign of this quantity. If you put your arrow here, then and then do this B dot dl, and then you ask what is this I enclosed, we will say that the positive side is ours because it is anti-clockwise from our side, negative side is behind the board, and the current coming from the negative side to the positive side crossing this, that has to be written here. So, all these things are to be remembered when you are using this. So, for getting that relation, what we will do, we will take a loop of this kind. This is the point above the surface, we will draw a line here, and then this below the surface we draw a line here, parallel line, and then we will connect it, and these lines will be perpendicular to the surface. These lines are parallel to the surface in the direction of current, and these lines are perpendicular to the surface because this point is above and this point is below. So, we do have a model for that also. We have made this model. This is let us say this is our surface, and on this surface we have current. These arrows are showing the currents. This is the direction of current here, and then this is a point, this is a point, this is a point above the surface, and then on the other side we have similar point here below the surface. So, one point here, this is, if I make this surface horizontal, then this is above the surface and this is below the surface. Now, from this point I draw a line, and this line is parallel to the current. This is the current direction and this is the line, and similarly from this point we draw a line and that is parallel to the current, and then we join these ends, these vertical ends. So, these are the lines which are perpendicular to the surface. Okay. So, that is it. So, the closed loop is ready, one arm here to here, then the second arm is going perpendicular to the surface, crossing the surface, coming out below the surface here, and then reaches here. Then the loop continues this way and it reaches here, and then it continues, and then perpendicular to the surface it goes like this, pierces through the surface and then comes here. So, that is our closed loop. This is the loop on which we will be applying Ampere's law, right. So, in the diagram, this line here is this line, and 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 the arrow is like from here to here, then from here to here, and then from here to here, and then from here to here. So, that is the kind of geometry that is here. Now, B dot dl, this is the first, let us say arrow is this way, and this is the first arm, second arm, third arm and fourth arm. So, first arm, this arrow is like this. So, this one B dot dl, let us say this direction is x direction. So, unit vector is I cap. So, B dot dl, this will be B dot dl I cap, right. This is B dot dl I cap, dl vector is dl I cap, and this is B dot I cap and then dl, and this is the component of B in the I cap direction. When you take the dot product with a unit vector, you get the component of the vector in that direction. So, this is the component of magnetic field B in this direction. This is tangential direction, and parallel to the current, right. So, we write let us say here the magnetic field is B1. So, first arm, so B1 and component, tangential component, and that tangential component is parallel to the current. This tangent is parallel to the current, and then the length dl. So, delta L. This is on the first arm. Okay. Now, second arm. Second arm is this one, this length. Now, once again the 2 points that we have taken, some here a point and here a point. above the surface and below the surface. They are just above and just below. Okay, these points are just above, this point is just above and this is just below. That means length of this vertical line, is nearly 0. And if the length itself is 0, then B dot dl will be anyway 0. So, on the second arm, second arm, since delta L is going to 0, we are talking of just above and just below, therefore, this B dot dl is 0 on the second arm. Third arm, here B dot dl is B and dot dl will be dl in minus I cap direction, because on the closed curve you have to draw your direction, arrow directions. So, here the arrow direction is left to right, here the arrow direction has to be right to left, and therefore, this dl vector is in the negative x direction, and hence we can write it as dl minus I cap, and that means it is minus B and dot I cap is component of B2, since I am now here below B3 you can write, but nevertheless B2, and then minus B2 tangential component and parallel, it is this, and then into delta L. So, on this, since dl is in negative x direction, and therefore, B dot dl will be the component of magnetic field in that tangential direction and with a negative sign, and then this dl, that is it. Now, fourth arm is 0, it is 0, this B dot dl is 0, because the length itself is going to 0. What is the total? B dot dl? This circle means now I am talking of everything, the entire loop. So, it is B1 and tangential parallel to the current, this one, delta L, and minus B2 T parallel to the current, delta L. 0, 0, this one and this one, add, you get this. That is our left hand side. Right hand side, how much current is crossing the area enclosed by the loop that we had taken. So, our loop is here, this is our loop, going from here to here, then here to down here, then going tangentially here and coming, and look at the area enclosed by this loop, and remember your current is this way, your current is going this way, and this is the area. So, is any current crossing the negative side of area to positive side of area, crossing this surface? Nothing. The current is going tangentially this way, this current is going this way, this current is nothing, no component, no current is going perpendicular to this area, no current is piercing this area, no current is crossing this area. So, that area I enclosed, current enclosed by this this area is 0. Okay. So, therefore, this right hand side here is 0, this is 0, I enclosed is 0, and hence B1 T parallel is equal to B2 T parallel. The tangential component of magnetic field, tangential to what? Tangential to that surface, and since there are many tangents, we have to specify which tangent. Therefore, we are saying tangent in the direction of current. So, that component will be continuous, that component will not change. So, that is our another boundary condition. Then comes the tangential direction perpendicular to the current. So, if this is tangential direction, if the current is going this way, then perpendicular to this, again parallel to the surface, this line is in the surface itself, perpendicular to the current, then this whole line is now slightly above the surface, and then slightly below the surface you have to draw another line and then join and make that loop. Okay, so I do have this model for that also. See, the current is going this way, this is the surface, current is going this way, and this is the surface. Now, this line above the surface, it will be horizontal, will be like this. So, this we will be saying above and this below. So, above the surface, and then this line is parallel to this surface. This line is parallel to the surface, this line is perpendicular to the surface, this line is perpendicular to the surface, this is parallel to the surface, but the current is along these lines, current is along these lines, and this line is perpendicular to that. So, it is tangential direction, but perpendicular to the current, and in this direction I have drawn a line parallel to the surface, perpendicular to the current, above the surface, and similarly below the surface, parallel to this. Here this line is once again parallel to the surface. So, it is tangential, but then current is going this way, and therefore, it is perpendicular to the current. So, that is the situation here, and once again you do all these analysis, and if you do this B dot dl here, dl vector is now in this direction. So, if this is x, if this is x and this is z, then what is this direction? What is this direction? This direction will be, if your x is here and z is here, z cross x. So, this direction is your y direction. So, let us take the loop this way, from here to here, and then from here to here, and then here to here, and here to here. So, that this will be this B dot dl. So, where do I do? Here. So, now we have the plane is here, the current is this way, and our loop is this way. Our loop is this way, this is up and this is down, right, and you can take any direction. If this is x direction, and let us say this is y direction and this is z direction, we take the loop this way. Let us take this loop this way, does not matter, I can take the other way also, same results. Then arm number 1, arm number 2, arm number 3, arm number 4. What is B dot dl? What is dl? This dl, this is dl, this is dl, this is dl. So, let us say it is, if this is y direction and I am taking arrow this way, then it is B dot dl and minus j cap. So, it is minus b y and then this dl, and since it is all small thing, we write it minus by delta L. Then arm 2, 0. Why 0? Because that height itself, the length itself is going to 0, just above the surface, just below the surface. So, this is 0. Arm 3, just reverse of that, the dl is in this direction now. So, it will be by times delta L, and this actually you can write as minus bt, and this is bt, b2t or b1t, right, this is first arm. So, b1t and perpendicular to this current, and similarly this you can write as b, this is arm 3, so below, so b2 tangential and perpendicular delta L. So add everything, arm 4 is 0, add everything, in closed loop integration b dot dl is equal to b 2t perpendicular and minus b 2t b 1t perpendicular delta L. This is our left hand side, and what is our right hand side? How much is I enclosed? So once again look at this, look at this. Here is the area, this is the area bounded by this loop, and see the current directions. See the current directions. This current is piercing through this area, going from this side to that side. This current is going through this the area and from this side to that side. So yes, there is a current. There is a current which is going through this area bounded by this loop and from one side to the other side. And how much will be that? That will be K times delta L. K is the surface current density, and that is how we define current density. If you have a surface current, then perpendicular to the current you draw a line and then ask how much is the current going through that line, then divide by the length, and that is how we define K. So the current which is going is K times dl. So this should be equal to K times delta L and mu naught here, and that says that yes, this component is not continuous. This is not continuous, it is mu naught times K. So the tangential component is discontinuous. If they perpendicular to the current, that tangential, if you have a surface current, if you have a surface on which the surface current is going, and then you look at a point on one side of the surface, on other side of the surface, just above, just below, then the component of the magnetic field which is perpendicular to the current and tangential to the surface, that will be discontinuous, and it will suddenly change as you go from one side to other side, and the change will be mu naught K. Remember our large xy plane carrying current, and there we saw that if the current is represented by these dots so that it is coming towards us, then here the field, magnetic field was mu naught K by 2 in this direction, and here it was mu naught K by 2 in this direction. So this is current and this is the tangential component we are talking. So it is perpendicular to the current but tangential, parallel to the surface. You can see the change. It is mu naught K by 2 in this direction, and therefore if you write in this direction alone, it will be minus mu K by 2. So the change, the discontinuity, sudden change as you crossed from this side to that side, this is a thin surface, just a surface. So from this side to that side, the difference is mu naught K, that is this mu naught K. You can write this beautifully, and it will be something like this: B1 tangential and minus B2 tangential will be equal to mu naught times K vector. Let me put a vector here, and cross n cap. Okay, the component parallel to the current does not change, right? For components parallel to the current and parallel to the surface, so that does not change, and therefore if I say that this is the net component in the tangential direction, that means if I do not take this component parallel to the current, I do not take this component perpendicular to the current, but I take something in between, Suppose I take this line, this component, how much is this component changing from this side to that side? it's same as the change in this component, because here the change is 0. So, the net change is coming only from here. So, even if you do not write perpendicular and parallel and you just write tangential component, whatever tangent you wish you can take, parallel to the surface, any direction you take, this difference will be the same as this difference, and this you can write as mu naught k cross n. What is this n vector? This n vector, unit vector is, this is unit vector perpendicular to the surface, and there are two possibilities. If this is the surface, this is perpendicular and this is also perpendicular. So, perpendicular to the surface in the direction of side 1. You decide which side you want to call side 1, and then be consistent. Tangential component in that side, this one here, and this is the tangential component in side 2. So, whatever you decide side 1, that has to be written here, and side 2 will go here, and then this n cap is the unit vector perpendicular to the surface in the direction of side 1, and this, then this will be true. So, for normal component we had B1n is equal to B2n, and for tangential component, okay, you can put a vector also in that normal direction, and for tangential component you have B1t and minus, so this is okay, fine, this is equal to this, and then this is B2t here, and that is equal to mu naught k cross n. And you can also combine this, let me put minus here and equal to 0 here. What is this and plus this? What is this plus this? In the perpendicular direction, this is the component, and the tangential direction, this is the net component in the tangential direction, and you are combining, you are adding these two vectors, this vector and that vector, you are getting the resultant magnetic field. And similarly, this, add this one and this one, these two vectors, the B2, the normal component of B2 and the tangential component, and this tangential is now the resultant tangential direction, which you can have a component parallel to the current and perpendicular to the current. When you add these two, this one and this one, what do you get? You get the resultant B2 vector. So, you can also write this as, add these two. So, this will become B1 vector. Add these two, minus here, so minus, this will be B2 vector, and here 0 and here this, so mu naught k and then cross n cap. So, this relation contains everything, all information, one single relation. So, you can work with this, and then from here you derive all your things. But it is practically it is better to remember this separately. The normal component does not change, and then the tangential component changes, and the discontinuity is this much. And in the tangential component also, the component of the tangential component along the current, the component of the tangential component along the current direction, that does not change, and only the component tangential magnetic field component of that in the direction perpendicular to the current, that changes by this. So, these are the boundary conditions on magnetic field across a surface which may contain a surface current.